changes that are going on in your teams, please let me know. And I posted something yesterday. There's one person who is finishing up project 3 but is now on a 1-person team, and I'd like to combine him together with other people to form a team for project 4. And so if you'd like another person on your team, please let me know. And if people are leaving your team, please let me know. We've already talked about why it's a good idea to use project 2 code, but you can use our project 2 code, but you can use your own if you want to. And again, RBFM is not really the right fit for what you need to do in project 3. On the midterm, if you have questions, please let me know about the questions by today. We don't have to get them resolved by today, but please let me know about them by today. I know there already have been some questions, but if you have additional, again, please try to let me know by today, or let someone know by today. So we're now in the middle of talking about transactions, and we talked a whole lot about locking nodes last time. And there were these S locks, which are like read locks, and then the X locks, which are exclusive locks. And we talked about these notions of 2-phase locking and strict 2-phase locking last time. And the idea is that if a transaction wants to be able to read data, it gets an S lock, and if a transaction wants to modify data, then it gets an X lock. But with that's just what locking is about, and this is a way of trying to ensure serializability or other isolation properties that relate to some of the ACID stuff that we talked about, in particular a kind of isolation from the effects of other transactions. With 2PL, it's called 2-phase locking because you lock in 2 phases. There's a phase where you can get locks, and there's a phase where you release locks. And the general idea is in 2-phase locking that there's a growing phase where you can get more and more and more locks, however many locks you want to be able to obtain. And then there's a point where you no longer are getting any locks and you release locks. And in the second phase, you're releasing locks. You can't get any more locks. And the nice thing about operating with 2PL, with 2-phase locking, is it guarantees serializability. Basically, you're not getting any more locks after you start releasing locks, which means anybody who gets one of your locks after you has to basically come after you, and anybody whose locks whose locks were released before you started and where you got the locks, they actually have to go before you. So it's not a very hard thing to prove that this guarantees serializability. Anybody who released locks that you're using had to come before you, and anybody who got locks that you released had to come after you. And there can't be any arcs where somebody comes before you and somebody comes after you, because you're not grabbing any locks later. If you could grab a lock later, then there could end up being a conflict. But because where somebody would have to both become before and after you. But basically, because you grab all the locks, which prevents anybody else who conflicts with you, it prevents them from grabbing those same locks. Again, they had to release the locks before you could get them, the conflicting locks. And we went over this. S and S don't conflict, but S and X do conflict. So do X and X. Okay, read-write is a conflict, write-read is a conflict, write-write is a conflict. We went over that last time. So again, 2-phase locking guarantees serializability. That's all well and good. But serializability is not the only property that you want. There's another property that you would like to be able to have, which is called ACR, which means it stands for Avoid Cascading Rollbacks, which in the book and other places is referred to as Avoid Cascading Aborts, but the term rollback is used instead of abort. And has been for a long time. And with strict 2PL, it's not that you can start releasing locks whenever you want. The locks get released when the transaction's over, when it's either committed or rolled back. Okay? And that, of course, will guarantee serializability because strict 2PL is 2PL. You never grab any lock after you start releasing. So it's great, that's serializable, but it also guarantees the ACR, because what it does is it guarantees that nobody's gonna be able to look at any of your data until you're done with it. Remember, there are two possibilities: you've either committed or you rolled back. And if you've committed, then somebody who grabs a conflicting lock after you is gonna see the data that you changed. And if you rolled back, then they're gonna see the data without any of your changes in it. And so there is no cascading rollback possibility. And again, a cascading, if you have something which has the ACR property, it avoids cascading rollback, it's always recoverable. And just to remind you about recoverable, okay, recoverable is the schedule where you commit only after all the transactions that supply dirty data have committed. So if you have ACR, you're always recoverable because there is never going to be a cascading rollback. Anybody who supplied you with dirty data must have committed. So again, you're operating with strict two-phase commit. You have this ACR property that you're going to not be able to have, there will never be any cascading rollbacks that will arise. And again, you're going to end up being recoverable. And that's pretty obvious with strict 2PL because you're not going to use any dirty data from anybody. When you're operating with strict two-phase locking, then we know that you're never going to be reading any dirty data. With strict 2PL, there is no dirty data to be read. You'll either read data of a transaction that committed, or the transaction rolled back, you'll be reading data from previous transactions that committed. So that's what's going on. Okay? So this is the way, if you're having 2PL, you get to a lock point and then there's a shrinking phase. But when you're operating with strict 2PL, it's the end of the transaction, and that's the point at which you end up releasing locks. And again, I can't emphasize this too strongly. It's not that you wait to the end of the transaction to release locks. The picture's a little bit misleading. You wait until the transactions commit, in which case all of its changes are there. Or it's rollback, in which case none of its dirty data is there until that's happened. So it's a little bit stronger than the picture would show. So let's look at this transaction that we have, which we saw last time is not serializable. We went over this last time. We had two transactions. One's moving 100 from A to B, and the other is adding a 10% interest to both A and B. And if you have T1 doing its first part, and then T2 comes in and it does both of its things, then you're going to get something where we saw last time the results. We looked at the actual values. This is not going to give you something which corresponds to either T1 happening before T2 or T2 happening before T1. It's because, you know, the value that was changed in A gets the 10% increase. The value that wasn't changed in B gets the 10% increase. This is not going to be the same as T1, T2. It's not going to be the same as T2 then T1. So this is not going to be a serializable schedule. It doesn't correspond to either serial schedule. But what happens when we have locks? So again, here we're serving locks. And so we have T1 doing, you know, getting, the X of A is a notation that means I'm getting an exclusive lock on A. So I might get my read lock on A first, but here, let's suppose we get the exclusive lock on A, we read A, we write A. And now, what is T2 going to do? It wants to be able to get a read lock or an exclusive lock on A, and it can't. It can't get either the shared lock or the exclusive lock on A. So what's it going to do? It's going to sit around twiddling its thumbs waiting and saying, A, I want to be able to get A, I'm in queued, I want to be able to get access to A. It can't get access to A until T1 gives it up. And T1 will only give it up when it rolls back or commits. So it's sitting there waiting for a lock, whether it's a shared lock or an exclusive lock on A. And T1 is going to do its thing, okay, and it's going to go ahead and you know, get the exclusive lock on B and write B. And now, as part of the commit, and really after the commit is done, not before the commit, It's gonna do the unlock, that's the U. It's gonna release the exclusive lock on A, it's gonna release the exclusive lock on B. And again, emphasis, despite the way it looks on the slide, the commit happens before it unlocks it. It doesn't say, oh, I'm about to commit, I'm gonna unlock it, because nothing's real until it actually happens. Maybe not even then, but nothing is real until it happens. When you have a commit, the commit is durable. Until the commit has happened, nothing has occurred. And so, again, after it releases the locks, then T2 can proceed and read A and write A and do things with B and all the rest of that stuff. So you'll notice that this is gonna be serializable. Whoever was able to grab the lock on A first went first. The other guy went second. You're not gonna have a situation in which you have things happening out of order where it's not serializable, which is what the schedule on the left would do. So the schedule that has locks in it is gonna allow you to be able to get a serializable transaction because you have the locks that are going on. But I was asked last time about something called deadlocks. Because it's possible that I'm waiting for you and you're waiting for me. And neither of us is gonna be able to get done because we're waiting for the other person to complete. Deadlocks are a problem. So here we see a situation. The transaction 1 gets an exclusive lock on B. Cool, that's fine. Transaction 2 gets an exclusive lock on A. Sure, why not? That's fine. And now transaction 1 wants a shared lock on A. And we said before that if we're going for serializability, that you can't get X and S together. You can't read something that another transaction wrote, because it may or may not commit. It may be a fantasy, it may be real, you don't know. And so you can't get the shared lock on A, T1 can't get it, because T2 has an exclusive lock on A. Shared locks and shared locks are compatible, but shared and exclusive are not, and exclusive are not. And now you have B continuing its work, and it wants a shared lock on, you have T2 and it wants a shared lock on B. So T1 has an exclusive lock on A and wants B in shared mode. On the other hand, you have a situation where transaction 1 has an exclusive lock on B and wants a shared lock on A. Each one wants a lock on something that the other has in exclusive mode. So therefore they can't get it. You can't have X and S together. So basically you have a graph where T2 has, you have a situation where for transaction 2, it is waiting for B, but B won't be released until T1 commits or rolls back. So the graph shows T2 wants B, that's the arrow between T2 and B. T2 wants B, but B won't be released until T1 either commits or rolls, or until T1 commits or roll back. Because you saw over there, X of T1 of B, that says that T1 has the exclusive lock on B. On the other hand, T1 wants A, wants a shared lock on A. But A won't be available until T2 either commits or rolls back. So what's going on there? You've got a cycle in that graph. How does that cycle get broken? Nobody can make any progress. That's not good. So deadlocks could cause the system to wait forever. Not a very good thing to happen. And you either need to do one of two things. You either need to prevent deadlocks and make sure that they can't happen, or you need to detect the deadlock and break it when it happens, break it relatively quickly if possible. The simplest universal mechanism for this is, if you know how long approximately transactions are going to take, if you're waiting too long, your transaction, you're waiting too long for something, you simply get a timeout and you roll back and you wait a little while and you try again and hope that it doesn't happen again. And that's the simplest mechanism that's used. And if Deadlocks tend to be relatively rare. It tends to work pretty well. And there are more sophisticated methods that exist, and we'll talk about them. Another approach, by the way, that can be used is to detect that when somebody gets a lock, it's creating a cycle, and that cycle will then be a deadlock. So, for example, if you have a situation in which, you know, basically, when T2, there wasn't any problem when T1 was waiting for A, right? T1 wanted the shared lock on A. That's the thing over here. The thing that caused the cycle was this. So you would say, as soon as this thing happens, you say, oh no, I'm not going to allow that, and you could roll back, for example, transaction 2, because it would create the cycle there. So you could actually detect that the cycle gets created when you do this. This arc creates a cycle. But again, the more usual way is simply to detect it by a timeout, because it ends up being a lot simpler. The deadlocks always involve 2 transactions? No. It can involve 3 or 17. The cycles could be complicated. It could be, you know, 1 is waiting for 2, is waiting for 3, is waiting for ... is waiting for 17, is waiting for 1. The cycles could be arbitrarily long. This ends up being relatively complicated to, you know, prevent cycles, because every time you add an arc, it could be creating a cycle inside there. And again, there are some good algorithms for cycles, but it's still kind of complicated to be able to do, and not worth the bother compared to using timeout. So there is a notion of a precedence graph. This is a graph in which the cycle gets created. And so the precedence or serializability graph basically says nodes are committed transactions, and the conflicts correspond to arcs that end up existing. So let's look at what happens over here in this thing. This is a schedule for running T1 and T2, which isn't serializable. We saw that. We saw it can't be T1 before T2, it can't be T2 before T1. So if we look at this schedule, which cannot happen if we're operating with 2PL, or let's strip 2PL. This schedule would not be allowed with 2PL. But in this graph, you have something where basically there's a conflict between T1 and T2. And there's a conflict between T2 and T1. One of them, you know, conflicts on A and the other conflicts on B. So this is a graph which is not going to be serializable. There's a definition, sorry, lots of definitions in this discussion of conflict equivalent. 2 schedules or schedules, I like saying schedule, it sounds funny. 2 schedules are conflict equivalent if they have exactly the same set of actions for the transactions, and the conflicting actions are in the same order. What are conflicting actions? Actions where the lock modes would conflict with each other. Remember, XX is a conflict, XS is a conflict, but SS is not. Both XS and SX are a conflict, okay? So 2 schedules are conflict equivalent if the conflicting actions are in the same order. Non-conflicting actions, no problem. You can switch them around any which way you want. And now, what does it mean for a schedule to be conflict serializable? Okay, or graph to be conflict serializable? If it's going to be conflict equivalent to a serial schedule. So we've defined what conflict equivalent means, same actions and the conflicts are in the same order. And if there's something where you can change the schedule to something which is going to be conflict equivalent to it, and where that schedule is a serial schedule or schedule, then it's conflict serializable. It's serializable in a way that preserves the conflicts. We're not making the conflicts go away. So, okay, so here again we have our schedule with locks, and we showed you how you could deal with this by doing the wait. And here we had, the loop that goes on between T1 and T2 that we talked about, which is, again, not gonna be two-phase locking, it's not gonna be serializable. But in the schedule that we operated with locks over here, we're gonna be okay because T1 comes before T2. And this is gonna be something which is serializable. So here's the theorem, which we're not gonna prove. It's in the book, it's not very hard. It's a very easy proof. A graph is conflict serializable, meaning that it is equivalent based on maintaining the conflicts to a graph that is serializable. Okay, it is equivalent maintaining the actions and the conflicts to a graph that's serializable. If and only if that graph that we drew between transactions and their conflicts, if and only if that graph is acyclic. If there are cycles in the graph, it is not going to be conflict serializable. And next theorem, which again we've handled through, two-phase locking ensures that the precedence graph will be acyclic. And since it ensures that the precedent graph is acyclic, it's going to be conflict serializable, which again is going to give us a serializable schedule. So why do we bother with strict two-phase locking if we can get serializability by just making sure that the precedence graph is acyclic, and two-phase locking ensures that the precedence graph is acyclic? The reason is we care about this ACR property. Two-phase locking is nice, but it could mean that you have cascading rollbacks. You get a serializable sounds like it's good enough, but it's not good enough because it could be that you're using dirty data for, you're depending on a transaction that rolls back or that might roll back, which means that you would have to roll back as well, and that's not good. You shouldn't commit if somebody else would, somebody you depend on would end up rolling back. So here's the way, again, that you get strict 2PL. You hold the locks until the end of the transaction. And again, I'll emphasize, it's not that the transaction wants to end, it's that the transaction really has made all of its changes if it committed, and it made none of its changes. They went away if it didn't commit. So you end up having no right-right conflicts, no right-read conflicts. The reason you don't have any right-read conflicts is that if this guy who didn't commit, if this guy who rolled back, then the original data is back there. And so you can read the data that corresponded to the data before the fellow went forward. So again, the idea is you only read data that's committed data. You end up not having any conflicts on right, where one guy is updating data that corresponds to somebody else who hasn't committed yet. Nobody can see data, nobody can see uncommitted data, nobody can write over uncommitted data. You end up not having any conflicts between these things. It's just gonna end up being serializable, and there's nothing where you have to roll back because you use data from a transaction that hasn't committed and may never commit, and may end up running back. Now we're gonna say a little bit more about deadlocks. We saw this example of a deadlock situation, and I said that there are other techniques for being able to deal with it. So again, deadlocks can cause the system to wait forever. Again, you either need to detect the deadlock and break it or prevent deadlocks. So how do you detect a deadlock? You draw the block graph and you keep maintaining it as you go. And if there's a cycle in this graph of locks of who's waiting for what, so you do cycle detection. You keep doing cycle detection as you go. And cycles imply a deadlock, but it's an expensive thing to detect. It really is. You want to, basically, what in System R, getting a lock in System R took 7 instructions. You can do it in fewer than that now. But that was in the late 1970s. System R, you can do it in 7 instructions. Grabbing a lock should not be something that takes a long time. You want it to be really fast. If every time you want to grab a lock, you have to see, do I have a cycle? Well, there are good cycle detection algorithms, but cycle takes 7 instructions. You want it to be a really cheap thing to be able to do. So again, detecting based on a timeout is a much more common way of dealing with this, but there are other ways. okay? So basically, you can go ahead and every time that there is an edge added to the graph, you see whether it introduced a cycle. You could do that. I don't know of anybody who does that. Too complicated. But here's a simpler one. Question?
In operating systems for deadlock detection, we discussed an algorithm where we order the locks in some fashion, and then ensure that any process that requests locks always requests them.
Hierarchical locking, meaning you always go ahead and you have an alphabetical order on the locks. So if you want to get A, you can get A, but then if you want to get H, you can get H, and then if you want to get K, you can get K. But after you get K, you can't get G, right? Because that's a hierarchical lock. You always get things in the order, and that ends up preventing deadlocks. In relational database, you always know the order in which you want to be able to get the data that you want to be able to touch, and that you can define a sequence on accessing the data only in that order. That's really hard to do in a database. So having an alphabetical order on resources where you can avoid having a deadlock because you always get things in a fixed order according to a hierarchy, it's a neat idea. It doesn't correspond to the way most applications work. But there is another approach. As Obi-Wan said, there is another. Well, there are a couple of other approaches. Here's the other approach that you can use, and it's not the hierarchical locking. You assign a priority to your transactions. I'm more important than you. Elbows out. So basically, suppose that T1 is one of these big elbowed higher priority transactions. And it wants to get a lock, and poor little T2 is sitting there and it holds the lock, and it's not nearly as important. Then basically T1 can steal the lock from T2, which is going to mean that T2 will have to roll back. And T1 with the bully big elbows is going to be able to proceed because it now has the lock. The data has been rolled back to the data before T2 ended up doing any of its work. So T1 with the broad shoulders and the big bully elbows can continue to go forward. T2 rolls back. T2 waits a little while, maybe some exponential back off kind of thing, and it starts again. And maybe it's not going to get bullied the next time, but it's possible that it'll keep getting bullied all the way through. So the more important transaction gets to proceed and gets to finish up, assuming that everything goes forward, unless there's another more important transaction that shows up while T1 is operating. But this is another way of doing it. There's not going to be any kind of deadlock because whoever is more important will make sure there are no ties, right? There's nothing where two things are equal. You look at two transactions, one of them is always more important than the other. The more important one is going to be able to proceed, and that's the way of going forward. We'll talk about a couple of other variations of the technique a little bit later. You may recall from 180 that there are these 4 transactions levels. There's also snapshot isolation that we talked about, where with read uncommitted, you can have dirty reads, meaning you're reading uncommitted data that may never commit. But with the other levels, there's no read uncommitted, there are no dirty reads that go on. In the case of where you're operating without repeatable read, then you have a situation where you're always going to be able to read the same data as you go inside the same transaction. But there's also this thing which is called the phantom problem, which I'm going to talk about on the next slide. And basically, the nice thing about serializable is that it gets rid of all sorts of different problems. Before I go on and explain about the phantom problem, let me tell you again, well, first of all, let me tell you about the 2 advantages that serializable has with respect to repeatable reads. One of them is a phantom problem, which I'm about to get to on the next slide. But the other thing is that repeatable reads don't guarantee that you have serializability. I could read A, B, C, where A was after 5 transactions committed, and B was after 20 transactions committed. including some that changed A. And C is after 49 transactions completed, including transactions that changed A and B. So the data A, B, and C never existed at the same time. Every time I read A, I read the same value. Every time I read B, I read the same value. Every time I read C inside this transaction, I read the same value. But A, B, and C never existed together. Repeatable read does not guarantee that all the data existed at the same time. It doesn't guarantee that the same set of transactions completed before I read A, B, and C. There could be a whole bunch of different things that went on. But there's also this really annoying phantom problem. And again, here is an example of how this can occur. And again, we'll stick with sailors. Suppose that what I'm doing is I'm scanning the sailors and I want to find the oldest sailor who is rating 1 and the oldest sailor who is rating 2. Okay? And that's what T1 is doing. So assuming that at the start, the oldest sailor who is rating 1 has age 80, the oldest sailor with rating 2 has age 90, and you'll see why this is there, the second oldest sailor that has rating 2 is 85 years old. We have some fairly old sailors inside the sailing club. Okay? So now what T1 is going to do is it's going to find the sailors that have rating 1. It's doing some reading. And it's going to go ahead and read those tuples, and it's going to get a shared lock, a read lock on those tuples. And it goes ahead and it looks at all the people who have rating 1, it has shared locks on all of them. And it sees that the oldest sailor with rating 1 has age 80. Okay? Now, it's going to start work to find the oldest sailor with rating 2. And grab shared locks on those to find the oldest sailor with rating 2. But remember that we're interleaving lots of other transactions that are going on. And now speedy transaction T2, then it's going to be nasty. T2 is going to come in and it's going to do some stuff. It's going to go ahead and it's going to insert a tuple that has rating 1 and age 99. Is there a problem with doing that? No. That tuple wasn't locked by transaction 1 because it didn't exist. How do you lock something that doesn't exist? Okay. And it's also going to delete the oldest sailor with rating 2. That's the guy whose age is 90. We'll assume there's one guy whose age is 90. So it's going to put a tuple in, and it's going to get rid of a tuple. A sailor with rating 1 whose age is 99, a sailor with, and that gets inserted, and it deletes the sailor whose age is 90. So the new tuple is inserted by is inserted with rating 1 and age 99. That's going to be with an exclusive lock by T2. The guy that it inserted, rating 1, age 99. It's got an exclusive lock by T2. That was not locked by T1. T1 didn't see it. Okay? And T2 is going to put an exclusive lock on the rating 2 guy whose age is 90. No conflict. Right? No conflict between T1 and T2. You get read locks from T1, everything it read, but there's a new tuple that's being put in with rating 1 by T1, and there's a tuple that's being deleted by T2. It has exclusive locks on those guys, no conflict with T1. No conflict with T1. And now T2 commits, gets rid of all of its locks. It only had 2 of them, but it got rid of them. T1 finally decides to wake up again and go. Again, these things can be interleaved all sorts of interesting ways. And it's going to look at all the sailors with rating 2, and it's going to find the oldest sailor who is rating 2. What's it going to find as the age of the oldest sailor with rating 2? 85. Because the guy whose age was 90 got deleted. So the final answer produced by T1 is going to be the oldest sailor with rating 1 is 80. The oldest sailor with rating 2 is 85. There are only 2 serializable schedules when we have 2 transactions. It's T1, T2. Let me go over and then I'll take the question. It's T1, T2, and then T2, T1. If I did T1 before T2, when I started out, the oldest guy with the rating 1 was 80. The oldest guy with the rating 2 was 90. T1 before T2. But if I did T2 before T1, the oldest guy with the rating 1 would be 99, the new tuple that T2 put in with the rating 1. And the oldest guy with the rating 2 is going to be 85. So the answer could be 80-90 or 99-85. but it can't be 80, 85. Not if I have a serial schedule with either T1 before T2 or T2 before T1. But what was going on with locking? I locked everything with shared or exclusive locks. And now the question.
Wait, I thought locks were at the column level rather than the tuple level.
Locks are at the tuple level.
Oh, okay.
Locks are at the tuple level.
Thank you.
I am locking rows. You can play games with other sorts of approaches, but the approach that we're taking is locking rows. And the trouble is that if I don't lock the entire row, I can end up having something where, you know, a different column happens and it breaks serializability. So locking at column level ends up being not achieving what we want to achieve. It could be it's a logical lock at the row level. But even if I have a column database, it's a logical lock at the row level for following the state. Not at the column level, at the row level. So this wasn't serializable. Hey, I followed all the rules, but it still broke. Whose fault is that? The Phantom did it. What is going on here? What's the Phantom? T1 looked at all the data that had rating 1. It didn't lock the data that wasn't there. As I was walking on the stair, I met a man who wasn't there. He wasn't there again today. Oh, how I wish he'd go away. If I'm looking over all the data with rating 1 and I want serializability, I not only have to lock the stuff that's there, I have to lock the stuff that's not there. I have to lock everything that has rating 1, whether it's there or not. Because otherwise, phantoms can get introduced that destroy my serializability. So, well, let me just, I'm going to get to it, but let me just tell you this over here. The way that you end up doing this is you might go ahead and lock the whole table. You might go ahead, and this was an idea, I'm going to mention it later, that existed in SQL. You might go ahead and have what was called a predicate lock, where you lock the predicate rating equals 1. That ended up being very nice idea and unworkable in practice. But the thing that does work in practice is, suppose that you have an index on rating. Then what you can do is you can lock in the index the thing that corresponds to rating 1 so that nothing can end up getting inserted with rating 1. By the way, suppose that I was looking for something, I was looking at all the people whose salary is between, you know, $10 and $100. Then I could end up, if I have an index on salary, locking the things that correspond to $10 to $100. But it's a little bit tricky. For example, suppose that there's nobody who makes between $10 and $100. Then basically what ends up happening, I'm not going to go through the details, is you lock the first value that's after 100 inside the index, which basically says I can't put in something before this. Again, there are tricky things in how you end up having to implement this with locking. Locking something that isn't there is harder than you might think. Locking things that are there is a lot easier. Okay, so basically I have, it's supposed, for example, that I was trying to lock everything that has rating 1 and there isn't anything with rating 1, that I can put a lock corresponding to the next rating which says